This is really both myself and Chuck. I've got several of Chuck's slides, but I'll do the talking. And but as I said, don't hesitate to ask questions. And also, just wanted to let you know at the beginning that I'm not a solar scientist, so some of you out there may know more than I do about it, but we'll together hopefully get to the place where the sun as a target for this equipment is something that's also fun to look at, and know a little bit about what to look for if you don't already. I'm going to have to run this on the edit mode for PowerPoint because every time I try to put it into view mode, view slideshow, it crashes. I had this working before, but for some reason it's a little flaky now, so I hope you don't mind. It's going to be a little smaller with junk around it.
Is this a Windows box disguised as a Mac? Or...
There's some Windows in it. I think that corrupts it, yeah. So I'll be talking about the dynamic sun and the aspect of sunspots and how that affects what we see. The sunspot cycle, which is going to bite us as we're going through the years now. Solar storms, in particular, the things that we usually look for, and the types of solar storms, and finally, the solar and planetary interactions. Okay, so the sun is a lot more than just a big yellow ball there. I think you all know that it's a very dynamic body and constantly in turmoil, but it's not obvious from just seeing it day to day, nice and keeping us warm and so forth. But generally speaking, there's an awful lot going on there. In particular, down at the center of the thing is, of course, the fusion taking place. Hydrogen atoms fusing to become helium, releasing energy, releasing electromagnetic energy, which in turn can go out through the radiative zone of the sun. And the radiative zone is so dense, and the electromagnetic radiation received is bouncing around in there that it takes million years or so for the radiation to get out. Then it reaches the less dense parts of the sun where the plasma that's there can start to move around. And in that, what we call the convection zone, there the plasma is boiling up, cooling off, and going back down again, boiling up, cooling off, going back down again. So in the convection zone, there's a lot of movement going on, and if you see it as it comes out to the surface, then it comes out in the form of the granules that you see here. And if you take a time-lapse photo of that, the time-lapse will show that these are granules that look like boiling water. Okay, a whole bunch of boiling water. Each of those granules would be, the tops of them are about the size of Texas. So it's a fairly dynamic thing that's going on there. I have to, unfortunately, it's not as easy to switch from slide to slide in this mode. But the sun, as a plasma, gaseous type of body, can rotate and does rotate at different rates at different latitudes. So near the center, the rate of rotation is about 25 days. Near the poles, the rate of rotation is about 36 days. The reason that matters is if, for some reason, the sun had a uniform magnetic field, then with time and the differential rotation, the result would be that the magnetic field would be all jumbled up. because it gets carried along with the plasma. So the result is a very jumbled up, messed up magnetic field. But nonetheless, plasma moving in magnetic fields give off radio waves and other forms of electromagnetic radiation. In some places, the magnetic field gathers together into a concentrated area of magnetic field, and sometimes that results in sunspots, areas that are cooler than the surrounding photosphere, these being of the order of 4,000 or so degrees centigrade, which doesn't sound very cool, but the surrounding plasma is of the order of 6,000 degrees, so it's much more luminous than the sunspots, so consequently the sunspots appear dark. Nonetheless, there's an awful lot of energy going on around the sunspot area, and if you measure what's going on in the sunspot area in different wavelengths of light, such as ultraviolet, you can see some of the intensities of that particular radiation relative to where those sunspots are. It's not always sunspots in that location, but oftentimes is. And those are the kind of temperatures going on as a result. So the sunspots are kind of key to what's going on relative to the radio emission. And the sunspots come in cycles. Right now, we're at the time when the sun is reasonably active. And then year after year, each of these represents a year, okay? And so the sunspots vary in about an 11-year cycle. Right now, we're just past an active phase, and it should be getting quieter and quieter over the next few years, becoming very quiet and then starting to build up again in terms of activity. As a matter of fact, over the years, if you keep track of a sunspot number, which is not exactly counting them 1, 2, 3, but it's related to the number of sunspots there, you would get this 11-year cycle in the sunspot number plotted with time through the years. But there was this time period called the Wander minimum, during which there were practically no sunspots for about 50 or 60 years, and that corresponded to the time when there was an ice age, little ice age in Europe that was recorded, but I assume it was going on all over the world. So right now we have a reasonable solar cycle year, or cycle I should say, 11-year period. This one wasn't as big as the last one, but we're on the downside of it now. So now the solar activity will gradually decrease with time. Doesn't mean it'll be completely gone, but nonetheless, it's going to die down with time. Interesting aspect of what goes on, and I'm not sure how well you can see that since it was put on there in white, but these sunspots usually come in pairs, okay? North-south pairs where the field lines come out of the north, go into the south pair of sunspots in the northern hemisphere, and then in the southern hemisphere it's reversed where it's south-north, with the south pole leading in the direction of rotation, north pole leading here in the direction of rotation, roughly speaking. And as the cycle continues, as you go to more active cycle, these sunspots have an average tendency to get closer and closer to the equator. So these move up towards the equator, these move down towards the equator. If you plot these sunspot pairs with time, it creates what they call the butterfly diagram, which spots that gradually get closer to the equator, spots that gradually get closer to the equator together. It's sort of like a butterfly. And then when the cycle ends, you go through the minimum, you go back to the active cycle, then these pairs seem to switch in polarity. So there's really a 22-year cycle and not an 11-year cycle, because at the end of the 11-year cycle, then you've got the switched polarity, which is kind of a different situation. So overall, there's this 22-year cycle. As mentioned, these magnetic field lines form loops. And this, again, is a time-lapse photograph, but the loops are really quite immense relative to Earth on that scale. And so there's these constant magnetic field lines all over, a very chaotic situation. And as Baptiste mentioned earlier in his talk, some of the times these loops are going to connect to each other, and the result is a release in magnetic energy. And that release in magnetic energy will cause these loops to break, and then there will be an acceleration of electrons along this broken, what you might call a rubber band-like thing, so that it goes out into space, and these electrons are accelerated out into space, result being what we would call a solar flare. Electrons spiraling around that broken magnetic field line. Here's the connection, okay, an X point where they connect, and then suddenly are accelerated outward and towards the sun. So the solar flare is this quick release. I'll play it again, just. I know you're seeing all kinds of weird colors of the sun. I know you know it's not green or red, but sometimes they use false coloring to determine which wavelength of light that they're looking at for this particular video of the sun. So the solar flares are what causes this type 3 radio emission. I'll get to that a little bit more shortly. Okay. Occasionally, there's not just a release of electrons, there's a release of a large amount of plasma from the sun, a much more energetic effect that's called a coronal mass ejection. Again, here's the Earth to scale, and this is kind of so billions of tons of material plasma flowing off the sun all at once. Again, that causes a major shock going up out of the sun, but the electrons in this case are emitting at the edge of that shock as it moves outward, and this is plasma moving outward, so it can't move nearly as fast as the lightweight electrons going out. So consequently, this is a slower moving effect. Whereas in the solar flare, the electrons are going out very rapidly, moving, and they encounter lower magnetic field values as they go out. So consequently, you see in a type 3 emission that the radio waves go quickly through the frequencies, quickly down in frequency as they're going outward. Okay, so very quickly, you go across the spectrum in terms of these flares that you see. Whereas in a coronal mass ejection, the drift through the frequencies is a lot slower because of the fact that this material is a lot heavier. Okay? So here are type 3 emissions, very rapid movement through the frequencies, and then at the end, they start to slow down and spread out. So typical bunches of type 3s. There's one up here marked type 2 because it's got a slower drift rate, and type 2s are a lot more rare than type 3s. So it's not very often that you see the type 2s. Down here we have type 2s as well, where they're drifting slowly through the frequencies. Type 6 bursts are just a set of type 3s altogether, lots of them happening at once. So if you want to know a little bit more about type 3s and type 2s and so forth, one place to go is the NOAA Space Weather Center, where they keep track daily of the events that happen around the world. They have a number of observing antennas around the world, and they provide information on what was seen by these various observatories and what type of event they recognized. So here, for example, is a type 2 event, and it's called a /3, where the intensity is according to this. 1 is minor, 2 significant, 3 major. Okay, and they also have this as definitions of the various types of radio storms. They do not, however, have this type 1 definition in there. I took that from a paper by Dale Gary, who's an expert on such things, and I would recommend going to that paper to get more information about the type 2s, 3s, 4s, and so forth. But these are the definitions of the various types, and you go to this URL to get past and present records of what's happening from time to time. I won't go through, well, I guess I could put this briefly. This just represents a typical type 3 radio emission. So this was a type 3 emission that occurred before the video was started, and this is a type 3 taking place in real time. The noise on this is not very good, so I'm not going to play the sound. But this was at Greenbelt, Maryland, also in Pennsylvania with Jim Brown's setup, and also, what was the third one? Remember? I was trying to remember where the third one was. But this is typical of solar emissions in that they're very well correlated among stations that are widely separated. That's the usual case, not all the time, but, and the typical type 3 signature is this quick rise, slower fall off, sharp fin type of signature. So when you see that, it's often a type 3. And the classification of the flares is based upon the measurement of X-ray from the flare, and where the peak is on this solar flare, those X-ray flux measurement, that's what determines what you would call the flare, such as an M3 flare or an X1 flare. Note this is a logarithmic graph, and so each decade here is 10 times more powerful than the previous decade, and each of these is labeled by the letter A, B, C, M, X. And I'm not sure why they chose A, B, C, M, and X. Maybe somebody else knows that, but for some reason it skipped from C to M and then from M to X. But I guess an X flare sounds a lot more interesting than an E flare. But all you have to do is look at the peak and where that falls on the logarithmic scale. So, In this decade, that's an X1. In this decade, that's an M3. I think we've heard enough about sudden ionospheric disturbances here before, but on the radio Jove equipment, I'm sorry for the red on the light, it should be the other way around, but basically the baseline takes the sudden dip and then gradually recovers. On the spectrogram, sudden dip in the background and then gradual recovery. So sudden ionospheric disturbances are another thing to be watched for when you're monitoring the sun. So finally, as I said, the sun is in constant turmoil. And watch for the different types of radio bursts. Radio bursts do follow the sunspot cycle, so now's the time to be observing because it's going to get worse for a few years. The cyclotron or synchrotron emission mechanism are the usual expectations of what's causing the radiation, and from that we can learn about the solar interior, solar cycle, magnetic field strength, and so forth. So with that, I will finish.
In addition to this data, it's interesting to go to the Solar Dynamics Observatory website and play the 48-hour MPEG movie of real-time sun and compare it to the radio Jove output. And you can, it moves real fast, but if you're fast, you can stop the movie, and then it gives UTC time, and it can be correlated directly to radio Jove. And you can see, you can correlate the noise, well, the peaks, with the events that occur at that time.
Right. And I know one of the things that, well, a lot of the things that people do are to set up solar telescopes, optical telescopes, and try to catch a flare that's a visible light flare. And that's pretty spectacular when you can do that. Tom Ashcraft is the person I know that always likes to do that and often publishes what he sees when he does it.
Yeah. There was a mass ejection about the time that you were showing up there in June. It was quite spectacular, and the radio display was interesting.
Yeah, the CMEs can be very disruptive if they're aimed towards the Earth. But it's not very often that a real strong one is aimed towards the Earth. Question?
If we restricted ourselves in describing our ham receivers and transmitters to only the language of magnetic fields, I think we'd have trouble presenting what those circuits were doing. Why do we limit ourselves on the sun to only the language of magnetic fields and never speak of the electric currents that must be there?
Okay.
We're just amateurs out here.
And I'm joining you as an amateur as far as solar science. I guess in the same sense, to me they would be interrelated in some ways, but
Maxwell's equations.
yeah, it's always interrelated. But I mean, in terms of the the strength, for example, of a solar flare, you could measure it in terms of what, electrons per second or something like that. Is that what you mean?
I think the main difference is that when you look at magnetic loops on the sun, it's static, it's moving, but it's not a wave, it's not an electromagnetic wave. So it's a different, it's not the same.
It's a DC thing. You can use
There's no
VLA and take a look at a distant galaxy around it, and you can measure the current in that loop. It's a big DC current.
Yes, you would be measuring something, but not what you measure there. It's something different. It's another result that would be interesting, but it's something different than the radio emission.
Yeah, I'm not sure how easy it would be to measure the, the electricity moving in that loop.
Well, it has been done.
Yeah, I'm sure it has been done, but, usually they come in pairs, triplets, all kinds of things. I'm wondering how hard it would be to get a singlet type loop so you could be sure of what you're measuring in that particular loop. Any other questions?